Good afternoon and welcome to today's webinar on truly understanding hypothesis testing concepts, making a complex topic simple. I'm first going to go over a couple of logistical issues and then introduce our speaker and presenter, Rick Haynes. This webinar is scheduled for 1 hour. If we have a lot of questions, they could potentially go over the initial hour, but we will cover all of the content within the 1 hour window. We are using GoToWebinar and have all the participants muted, so please text in any questions you have throughout the webinar using the GoToWebinar system. We'll try and get those addressed at that time when they're relevant. If we do not get to your question, we'll definitely get it addressed at the end, but again, please feel free to text in your questions at any time. We are also recording this webinar. You will receive an email within 24 to 48 hours to get access to the recording. You will have a period of 14 days to view this recording. And you will also get a copy of the presentation itself, which will come by email as well. I will now introduce our speaker, Rick Haynes. Rick is a 20-year Lean and Six Sigma practitioner. He is our senior and lead master black belt. He has a career as certified as a master black belt, champion, and yellow belt, along with teaching and certifying professionals in all the Lean Six Sigma areas. His personal Lean Six Sigma work has spanned nearly all business types, manufacturing, transactional, along with research and development business. He is a master's degree statistician and taught statistics in the Penn State University system. He has worked in all levels of the business, from the entry level up to site engineering manager. So he will have a lot of insight to bring to us today about hypothesis testing, so I will now turn it over to him. Thanks again for joining.
Well, good morning, everybody. Oh, I got to hit play. All right. Thank you for joining it. Hypothesis test is not easy. You may have heard it. It's hard to pronounce sometimes, too. I find that even when I have done my student teaching and my actual monitored teaching, for some reason everybody who monitors a statistics teacher chooses to come in during the hypothesis test section because it is the most difficult to explain and work on. So I guess in all my years I've been doing this, I've been trying to make this topic easier to understand. Where I'm going to be speaking out of, the references I use for this stuff will be out of a book by the owner of our company, Integrated Enterprise Excellence, Volume 3. The book's available on Amazon. It is a complete reference to Lean Six Sigma, DMAIC processes, even the soft and hard skills. So let's move on. All right. Why are you here? You're here to understand hypothesis testing. My goal at the end is that you say, I understand this better than I ever have before. That's the only reason that I'm giving this, is to gain people that understanding. I'm going to start with a question, because we do this during webinars. And you're going to get the same exact question at the end, and I'm going to judge how much different the world changed. So I'd like you to estimate on there, pick on your screen, your current judgment of your understanding of hypothesis testing. From very low, you can get by. And if you pick the fourth one, you can sit here next to me in this webinar. I see you guys doing it. It looks like good enough to get by is where most of the people are. Now I'll give you another couple seconds to fill it out. Mallory, if you'd close it. And you guys should all see the results now. Over half of you are getting by. Now what's one nice thing about hypothesis testing is, it's some level, if you can find the right test and you can find a p-value on your computer, you will make the correct decision, whether or not you understand why. I'm hoping you'll go past that point and actually be able to understand what you're trading off and what's really happening with a hypothesis test. But we'll see at the end if this score gets better. And we were all taught this. If you're a Lean Six Sigma person, and I did talk to somebody who's in the webinar this morning who signed up, and they're just getting a statistics class right now, and they're coming to see this not for Lean Six Sigma, but just generally hypothesis testing. You know, that's still important. We've all taught this. We use it to make the decisions in the statistical testing. And I like at the bottom, we just got through the class enough to pass. But what is a hypothesis test? I'd like you to consider it more of a risk management type decision. what you're doing is you're going to make a decision, and you're going to wonder what the uncertainty or the risk of it is. Now, there's two pieces of hypothesis test, alpha risk and beta risk. Well, alpha risk is a complement of the confidence of your test. 5% alpha, 95% confidence. Now, beta risk, it's the opposite of the power, or the complement of it. 5% beta risk means 95% power. Let's try to talk about this without a picture yet. What is it in layman's terms? Well, I start out in statistical words. The real alpha risk is defined as the risk of rejecting the null hypothesis, H0, when there really is no change in the process. So and I'm going to do most of my work here with a t-test in my little pictures and diagrams that are coming up. But it would be sampling, you're assuming that the population changed for your alternate hypothesis, but you sample from the original population again, it's your chance of declaring the process changed when it didn't. So another word is the alpha risk is the risk of declaring a significant difference when and being wrong. So you're wrong to declare significance. And probably my favorite analogy for the U.S. people, the American court system is really a hypothesis test, where the alpha risk is the risk of a false conviction. And we talk about in the United States that the null hypothesis of a trial is you are innocent until proven guilty. So the alternate is guilt. The null is innocence. But at the end of a court case, we don't really declare innocence or guilt, even though they do say that on TV and in court sometimes. What they really do is they acquit you or convict you. Or conviction means I have rejected the null hypothesis, so I'm going to convict you. But acquittal is I failed to reject the null hypothesis, which would be innocence. So we deal with the alpha and the risk and the confidence a lot, but we don't often get into the beta risk. And I'm going to try to give an understanding of how that works too. Because the beta risk is the risk of, in other words, risking of failing to reject the null hypothesis when you should have. In other words, there was a change, but you did not detect it. So I could use again here. The beta risk is deciding that that the difference is non-significant and you're wrong. Or, in the court case, releasing a guilty person. Now, I guess in the U.S. we realize this happens all the time in court cases, but for some reason we don't believe that it happens to us when we're actually doing statistical testing. In my life and Lean Six Sigma, as Mallory spoke, I've been doing it a while. There is one time in my career I got beat by the beta risk. I actually ran a design of experiments and nothing was significant, and I kept going through this project. After a month, I hadn't solved it because I never found a cause. I turned it over to one of the people who worked for me. Their first test, that was a significant cause found, and they fixed the problem. And it was the same test I had run. The difference was I got caught. That factor showed non-significant when it really was. So I actually got bit on the beta risk. Well, let's talk about how we teach it now. You must all have seen something like this, right? Where we say that you make a conclusion, but there is a truth that is unknowable. And I'll say we don't know truth. Let's say you got a sample from history and you want to take a sample from your process now, and I want to know, has the process changed? If we're looking at means, it's a two-sample t-test. All right. We're going to conclude either the null hypothesis, no change, or the alternate, the process has changed, or the mean has changed. We don't know the truth. Never know it. So generally we talk about the type 1 error, the alpha risk, or the confidence, which is, again, for the confidence you say, you choose H0 when H0 is really the true condition. When you choose the alternate or reject the null hypothesis, but the process had not changed, that's your alpha risk, your type 1 error. Now this chart's the one I've always taught with, but I don't like the proportioning of it. Let's go to the next slide. Look at a little bit different. Really, it should look something like this for the hypothesis. Your confidence is 95%, your alpha risk is small. That's what we're doing in most of our testing. We don't look much at power. Now, you'll see I've got a little block on the right that says no sample size and power has been determined before the test. I know this is, I don't know, nerdy, who cares, subtle, whatever you want to call it. But unless you've used a sample size calculator before a hypothesis test, you can make no estimate of the beta risk. Because the beta risk and the power of a test is really a function of risk after I've decided the sample size that I'm going to choose before I make the decision. If you just choose all the data you have, you cannot estimate a true beta risk just because it's no longer a sample, it's 100%. But if I go past this, and let's say you were able to use a sample size calculator, I think this picture shows the proportions a little bit better. You're trying to pick a sample size then to minimize the beta risk or increase the power. Okay. Now you're going, I paid just to see stuff I saw in class. Now here's where we're actually going to do something different. I'm going to, this may be a little tough, and I'll try to pause at times, but I'm going to go through, I think, 4 different programs to give you, try to make hypothesis test real. So first of all, I'm going to go to software called Notate, which is really just a desktop or a little whiteboard, and the wrong picture's up. This is the one we talked about, the standard hypothesis test diagram. What we're really doing here, and this allows me to draw on it, you're looking at, you took a sample, and your sample concluded either this or this, and I make a point, but we don't know what's happening over here. So generally it's one side or the other, so you pick, say I pick HO through this, there's a probability of being correct, but there's also a probability of having an error if it could have changed. I'll show you the weighted one I talked about. Now this one looks a little better, but really what we're looking at is, let's say you've got a sample, and it's going to be a sideways histogram if I can draw it well. There we go. Really what you have is a distribution here. This is what my sample distribution of my sampling statistic, in this case a mean, and we're looking at, if it really is at this point, the beta risk is still the area under the curve of the shifted data. All right? Where the decision point is the line. Now, I want to show you, I'm going to go over to a little movie I made of this from a software called Fathom, the teaching software that makes graphics. What we have here is, I'm trying to describe here a t-test. Now what we have here is, the mean is 0, standard deviation is 1, I have an n equals 25 samples. This is the histogram, or the curve of a t-value. Well, see if I can spell. But what's the standard deviation of the mean for a sample size of 25? Well, again, it's S divided by the square root of n, well, n, which would be 25, and I picked that because I can do that one in my head, so it's really 1 over 5 in this case. All right, that equals the standard error of the mean, 1/5. What I put right here, this is the decision point on a 95% test, which would be the t-value. So what would be this point here? Now, if you remember how to do this by hand, I'll show you. Something we all had to learn at one point. I got to go to Excel. And I have stat tables. They're all built in Excel. Now, if you're interested in this, they are available on our website. If you just want to see how to do them in Excel. But this is the t-distribution, two-sided table. I have n equals 25, so how many degrees of freedom? I know you're all thinking 24. I want a 5% test right here. My number is 2.064. So let me go back to this. So if I go 2.064 divided by square root of n, which is 5 there, it comes up with, and I can't do this in my head, so I did it ahead of time, but 4128. Oh, come on, get back. 28. What that is the t-value, which is 2.064 standard deviations from the mean, is where significance is for this t-value. So what's the standard error of the mean? Well, it's s, which was 1 over the square root of n5. So I end up with 4.128, which is this number right here. Now I can actually run this little picture here, and what you'll watch is, if it works, there you go. What you see is it's showing what distribution 2 would be in a t-test. What I've got here is this area right here. Don't know how this will work with a movie, but that is the 95%, 5% alpha risk. What we've got here is, if this is the null hypothesis, this is what your difference really is in your alternate sample, the area to the left of this line is really your beta risk, where this is the power of your test. So what you see, and if you got taught by us in this topic, you find that sample size is a function of the confidence, the power, and the standard deviation. So we set the standard deviation to 1. I'm going to run the simulation again, but as you can see, as the means get further away, the risk that you will miss the change is smaller if you look to the left of this curve. So we call this the power. If I can make a picture of it and color, I won't worry about it right now. But this is the beta risk. This would be the power. This is the confidence, and this is the alpha risk, given an alternate hypothesis of a change of means. So if you put in your sample size calculator that you wanted to change it this far, that's what you'd get. All right? That's one way to look at it. Don't be unhappy if you didn't get the whole picture. We're going to probably cover this 4 different ways. All right? So that's talking about where the alpha and the beta and the confidence and the power come from. But they're based on an assumption that, in this case, if the mean was, and if I look at my picture, it's somewhere around 0.7 to 0.8 in the alternate hypothesis, and the standard deviation is really 1, my test to distinguish the difference would have a power, I guess that's, say, 10%, or 90%, and beta risk of 10% just by looking at the curves. And what this gets to, and I'm going to go to the next little weighted picture, I think this is a better picture of what that confidence interval or the hypothesis test little diagram should be. Because in reality, what you have is, I got to go over here and pick my pen again. This would be the null hypothesis, some distribution like this of the mean. That's a t-distribution. That this would be our decision point right here, and here's my 5%. Well, when I'm going to use a sample size calculator, I said, well, I think the mean is somewhere over here. Say the same standard deviation. This is what I assume the real new population looks like. Use the art, but this is my alternate hypothesis. Given the same decision point, if I am right, this is where it used to be, H0, this is where it is, the alternate, I have this much risk that I won't detect the change, because I can randomly get a sample anywhere in this area, and this is the percent of the probability that I will get the right answer that the process shifted. So that's another way to look at what we're doing. Now, I know nobody's put a question in. Please ask. I'd like you to ask questions about, because to learn this, you need to ask and get, even if it's reassurance that you have the right answer. Just like in class, ask the question, because there's some other shy person on this list that's afraid to ask the same question. All right? So given those, now I'm going to go look at, that's just shifting the mean. Let me go back and look at my Fathom software. Now this, I'll let it go. This is going to take a minute to come up. It's a little finer. This is the teaching software that dynamically graphs. The question, what comes up to your, or how does sample size impact your hypothesis test? What you see here in the lower right of this, these are my original distributions of data. I'm assuming this, the one the dots on, the bluish one, which is centered at 0, is my null hypothesis. If my alternate hypothesis is the second distribution, I can see it's got a mean of 0.6 in this case. The standard deviation is listed here at 1. All right. What am I doing now as I adjust this stuff? Now I can see over here, these are my distribution of t-values, or the distribution of the means from sampling from the null hypothesis distribution, mean of 0. Where the one on the right is the sampling of the means from the alternate hypothesis. Now I can see what happens when the standard deviation goes down. As you notice, this line here changes because now it's still 2.064 times divided by the standard deviation of the means. But I can see as I lower the standard deviation of my data, the 5% of the curve stays here, but the probability of this in the alternate hypothesis curve becomes smaller. When you have a larger standard deviation, you see that the 5% is still 5%, but this line moved based on your standard deviation in your confidence and your alpha test. But the power changed dramatically. The power is this side of the curve. So still, given a belief that my process is here with a mean of 0.6, chances are I may not notice the difference in the change. All right.
We have a question.
Oh, wonderful.
Going back to the t calculation, can you explain why you divided by 5?
Yes, I can. Let me go back to where I can draw. I'll get myself a new graph here to draw. Okay. What we say, it's called the central limit theorem. And by the way, this is a limitation of my handwriting, not the tools I'm using. Central limit theorem. All data that's average tends to be more normally distributed than the original data. But it also tells us that the standard deviation of the data, we'll call that S. But what's the standard? If I take multiple samples of that data, I'll get a mean of each sample. Or call it X bar, average each sample. That average also has a distribution. The distribution of the means is a t-distribution. Comes up, there's a whole story behind it, but a t-distribution is the distribution of means of samples taken from a normal from any distribution. And so the next question, they call it standard error. Standard error equals the standard deviation of means, all right, which is equal to, by definition in this theorem, S, standard deviation of the data, divided by the square root of n, not n minus 1, n. So that's what, in the case I gave before, I had a sample size of 25. So when I chose by my data distribution, S equals 1 for this test, n equals 25. So it said the standard error of the means would be 1 over the square root of 25, which equals 1 over 5. Now when I went back to this drawing, it was the movie one, what I was saying that this is the distribution of the samples of means taken from this distribution with a mean of 0 and a standard deviation of 1. So you can see 3 standard deviations out is really, it's really 1 over the square root of 5 because I have a sample size of 25. So that's how I got this. This is really a distribution. It looks like a normal distribution with a standard deviation of 1 over the square root of 5. But now to find the t-value for this distribution, I went and saw from the t-table it's 2.064 for a two-sided 5% test. So I multiply that times the standard deviation, which becomes my t-value to come over here, which was 2.064 divided by, or really times the standard deviation of my t's, which was 1 over the square root of 5, 1 over 5, which came to this. Now, I didn't draw well, but I hope that covered the point.
Thank you, Rick. The next question was, there was a good analogy with the court system. How do you apply the mechanics of the calculation illustrated with example of court case?
I would like to delay that till the end. I would rather discuss that after I've covered a couple more points. So I guess I'm asking your permission to wait to answer, and you don't have a choice. We're going to cover it in a minute because there's a couple points I want to cover to really make that distinction well. And it does fit, by the way. So go back where I was. I showed the fathom. Next one is let's actually try this in Minitab. Now, I'm a Minitab user. So I'm going to go to Minitab. I'm going to do stat, power, and sample size for a 2-sample t-test. All right? My sample size I'm using this example is 25. Now, I've got to pick a power. Now, we did a survey in our company about all the instructors for Lean Six Sigma and others. What's the power that they've used back in business? Because all of us have really had a job before this. And we got numbers from Forrest Breifogel, the owner, who used 95% power at IBM in the design world, down to a couple of us, and I was one that we used 0.8 or 80% power in all of our testing. So I picked 0.8 for this example. I'm going to assume a standard deviation of 1. I'm going to solve for the difference that has a power of 0.8 when I push the options. I'm choosing a not equal alternate with a 5% alpha. So really a two-sided 95% confidence test. N will be 25 in my samples, and I want a power of 0.8. So then I hit OK. Move this chart out of the way. And it tells me right here that with 80% power and 95% confidence, I will detect a shift of 0.809 in the mean. So since I chose a standard deviation of 1, I can consider that as really, call it an 81% of 1 sigma shift, and it's detectable with a sample of 25. Which means that I will detect, if it really changed that far, I'll only miss it 5% of the time. That's what the alpha risk tells me. So if it didn't change, I'll miss it 5% of the time. But if it really did change 0.81 sigma, then I will fail to detect it only 20% of the time, which is my beta risk. Now, given that, I'm going to now use another software, which is called, it's an Excel add-in called At Risk. Now, there's other ones out there, but this is my preference. The Monte Carlo sampling program. Been using it for years for things like this. How do you know what's happening? And I think when I was preparing for a project about a year ago, I found this out using the At Risk software, trying to figure out what do p-value distributions look like. Up till now, we were talking about p-values, distribution of means. But what about p-values? So what I did is I created a spreadsheet that has one sample that's got a mean of 0 and a standard deviation of 1. It's what I've chosen for it. And if I scroll down, there's 25 of them. See 25? Then what I did is I shifted it this 0.8087 sigma. So it should have a mean around 0.8, and standard deviation was unchanged, it should be around 1. Now, using the at-risk software, if you can resolve it on your screen, I'm really telling the software to pick the mean and standard deviation from these two cells here. I click to see the colors. So this is random numbers with a mean of 0 and a standard deviation of 1. It'll take that, calculate an average and a standard deviation. Now the system will take those averages and then do stuff with it. Well, here is my shift. In this case, I took the same standard deviation, but I added a shift of 0.808 to the mean. Over here, I compute the difference between the two samples if they're shifted. So I'm going to collect from all these random samples how many times it's sampled. For each sample, how far apart were the two means and samples of 25. But to have fun, I also, here's with no shift. So I really resampled the same distribution. Then a half sigma shift, a 1 sigma shift, a 1.5 sigma shift. So what I'm really doing is, if you remember that little diagram, if I go back over to Fathom, what I'm really sampling is a mean of 0, which means it's right on top, then a 0.808, which would be 2 samples. So I'm taking random samples of those means, and you can see from the bell curve, a lot of these are going to be to the left of the decision point. But I also did a 1 sigma shift, a 1.5, and look what's happening. You know, that was a little far, but you realize if the distribution's way over here, I may still only have a 5% chance of failing to reject the null, but the power is really huge on these. There's next to no chance that I will not reject it. So think about this. This is what I will get my samples from the test to, and that's the end I'm going to do. So let's go back and run this simulation. All right, I've set it all up. It's going to run 10,000 times, and it's going to accumulate the shift values and all the p-values. Now, this should pop up on your screen. You may not see it update well on your GoToMeeting, but it'll catch up when it's done. So it's running through here. Mine says it's, I'll give you a minute to look at it. What we have here, let's look at each of these output charts. Now, I'll start with the pictures, and then I'll start with the table of numbers. What I have here is, I wanted to look at, for an x of 0, I'll put a 0 in. It's a little calculator. What's the probability of being less than 0 when I have a difference of no shift? So this is comparing 2 samples that have the same population, a mean of 0 and a standard deviation of 1. This is the distribution of my differences. Notice, about half, 50.3%, are above 0, and half are below, which is what you'd expect if you take 2 samples from the same population, right? Sounds good to me. Let's go then look at, and that's what it says here. For 0, there's 49.6 below it. If I look at the shifted one, now this is the one I used my sample size calculator for. I moved it 0.8087 units higher. So I sampled the standard, the one at 0 and the one at 0.808, and then accumulated 10,000 differences by subtracting the means. What you'll notice is, here's the distribution of differences. It looks nice, and by the way, it's a t-distribution. But look what percent of those fell below 0, which is my null hypothesis. Well, 2%, 0.2 or 20%, but that makes sense because my sample size calculator said that if I use 25 and I shifted 0.8087, that I would get a power of 80% or a beta risk of 20%. So there I'm getting, with the simulation, I verified theory. I think that's the power of these Monte Carlo simulators, such as at risk. So 20%. Now, if I put my 0 back into this one, I can actually use a little calculator built in. It says, on average, should be about, it came out around 21%, which is still very close to my power estimate. Now let's look at the other one. So we've seen what 0 is. And now I'm going to show you what to me was the most, I guess I was so excited about this, I called people and told them that I found it. If I looked at the p-value of a t-test when sampling the same distribution twice, all right? Now, if everything's right, 5% of the time, I should assume that there was a change. 95% of the time, I should fail to reject the null hypothesis. Now, what's interesting, if I look at all the, this is a distribution of all the p-values I get from 10,000 samples of 25 from the same distribution. What you notice is, of the 5% p-value point, 4.8% of them are less than 5%. Now, what you're seeing here, this really is a uniform distribution, which after a whole bunch of playing with at risk, I found that p-values, if the null hypothesis is true, you always get a uniform distribution, which means randomly, 1 in 20, or about 5% of all your tests will have a p-value less than 5%. Now, I was dumbfounded by it, and I sat down and pencil and paper and realized that it had to be that way or the p-value was not doing what we wanted. All right. Pause for a minute, you'd ponder that. So if I go back now and I put in here 5%, 0.05, my calculator, it predicts, in this case, around 5.1% of the data will be below a value of 0.05. Oh, I didn't put 0.05 in, though. Put something different. There we go, 4.81, same as I got in the picture. But let's say, what happens if the standard or if the mean had shifted half a standard deviation? Here's the interesting one. We chose to have a power with a shift of 0.8, but what if it's 0.5 shift? So half a sigma. Can we make this a little bigger? Look what it had here. Below 5%, 14.7% of my p-values would now show a significant shift. But 85% of the samples I would take, I would fail to reject the null hypothesis. That's what really this picture is looking at. So as the mean starts to shift, you notice there's a higher percentage of the p-values will fall below 5%. Now this is why we're looking, but notice some of them still would reject the null hypothesis even though my power wasn't there. So yeah, you can still reject the change even though you haven't moved it very much. How about the next step? 1 sigma. This is slightly above what we said our power would be at 0.8. Where did the chart go? There it is. Bring it over. Now look what it is. If I had shifted 1 standard deviation with a sample size of 25 from both populations, 93.4% of my p-values that would come up from that test, I would reject the null hypothesis. But there's still a 6% chance that I can sample from those 2 distributions and fail to reject the null hypothesis. We do the last one, which is a 1.5 shift. After this, the numbers get so small they're not worth looking at. I guess that's not fair. They're telling here. So look at it. If I get a shift of 1.5 sigma, I'm going to reject the null hypothesis 99.9% of the time. This may be a bit confusing because what am I doing? I'm using the word percent twice. One is percent risk, which is your alpha risk and your beta risk. But the other, the 0.05, is what probability will you of getting a p-value falling in there. So it's really, you have a probability of rejecting the null hypothesis 99.9% of the time. Now this isn't clear just from the math. You really need a simulator to do a whole bunch of samples. Again, I used 10,000. 100 wasn't enough, but 10,000 was. I'm hoping I'm showing what's happening with the idea of what the p-value means. And even in this case, you still have a 1 in 100 chance, 1 in 1,000 chance that you'll fail to reject the null hypothesis. I mean, that you will reject the null. There you go, fail to reject it when you should have rejected it. So yeah, I stumble over these words still. I've been doing this for years. So that's what the simulator does. All right. I was going to show one more. See how am I doing for time? I'm good. An interesting one that we do a lot in Lean Six Sigma. And I got to close this. I've already got it saved. But what I'm going to do is open another one. All the ones that are open at the time, they all end up running the simulation. I didn't want to run both of these. This is an Anderson-Darling test of normality. What I have here is a random set of data. I think there's 100 of them. 100 data points, normal distribution, the mean of 10 and the standard deviation of 3, and I'm going to test them for normality. All right. What's my null hypothesis? The data is normally distributed. But guess what? I know it is because I made it that way. You can see with my risk normal, I've chosen it to be normally distributed. And then, what's the probability? And then I'm going to collect on it the p-value for the Anderson-Darling test. Let's run the simulation. Again, 10,000. What's it come up with? If I told you the truth before, that if the null hypothesis is true, the p-value is a uniform distribution. Got a lot of data points to collect here and calculate, so it takes a little bit longer than the last one. Yeah, I guess it's taken longer than I expected, but what will come through is if I'm right, if the null hypothesis is true, 5% of my values will fall below 5%. There it goes. I probably shouldn't have done 10,000 because this is an awful lot more random numbers. I'll stop it halfway through and I'll still get my result. Sometimes you can ask too much of your random number generator. There we go, big jump there. The software actually shares between the CPUs to get you four. I got 4 cores supposedly, so it gives me 4 random numbers in each clock turn. That should be enough to get by. Let's just stop it. All right, stop, yes. Now let's look at my chart. Once it's done, these are my p-values. Oh, there you go, I hit it. And there's randomly just a couple high points here. But if you look again, the 5% point, 5% of them were below 5. This shows that even normally distributed data, 5% of the time, you will get a p-value below 5%. But this phenomena will happen on every single time you test a hypothesis test. You will get a 5% chance you will, if the null hypothesis is true, you'll reject. Going back to my whiteboard, that's how I get back to this. This is really what you're looking at. If it really is over here, there is some percent of the time. This is where the part that the null hypothesis would have been accepted if you got a sample there. So I hope that's another way to look at it. I'm going to finish up then, as I'm getting down here, with a way we teach this. This came from a good friend of mine, Dave Berenson. As I struggled with one class that we were co-teaching about how do I make this happen. This may or may not work for you, but what I have here is a plot of all the potential p-values. Think of it like that histogram or the uniform distribution. But every test will get a p-value between 1 and 0. Now, we have made a decision point of 5%. If the p-value is less than 5%, as in this range, we will reject the null. If it's in this range, we will fail to reject. Now, I'm going to lead back to the court case with this slide. So really, every time we sample, we get this whole range of p-values. Now, if the null hypothesis is true, exactly 5% of them fall in this range and 95% fall here. But as we saw, as the mean really shifts in a t-test, you get a smaller fraction in this range and a bigger part of them here, and that's what's really making our decision to reject the null or not. The thumb rule I was always taught is this point comes somewhere around a t-value of 2, which is really about 2 standard deviations of the mean away from the mean. And again, that's still a function of the standard deviation of n. All right? The way to teach it is where every decision falls, the p-value falls in this range. If it's in this range, reject. In other words, declare significance. If it's in this range, fail to reject and understand the risk. Now let's talk from here about to go back to the court case one. Court cases in the United States, we're going to assume it's a jury case because it makes sense. What's the size of the jury becomes the sample size. I think civil cases here in Texas can have 4 to 6 people in some cases. Most criminal cases have higher numbers, and capital murder cases always have 12. Now, why a bigger sample size? Well, bigger N, you get better discrimination. Now, in civil cases, you need a majority to declare a winner. But again, what's the risk of being wrong? Nothing, because it'll always get appealed. But in criminal cases, let's pick a criminal case for a felony. In some places, they can convict with the majority of the jurors choosing guilt. That would lead to a conviction. So because you allow some people to choose not guilty, what you're looking at is part of the risk assessment. Now, when we go to capital murder cases, and I think everywhere in the United States, it's 12 juries, and you need a unanimous decision for capital murder, especially in cases that could lead to the death penalty. But what have we done? If you think about it as an attribute sample, 12 out of 12 is a lot harder to get that observation than if we went to a majority, which would be 7 out of 12. So again, we're managing the risk by how many we require to call guilty out of the jury and the sample size of the jury. Now that's how it goes together. Because if you think about it, when we're innocent until proven guilty, big sample, and if we require, for capital murder, 12 people to all convict, there's very little chance of that beta, or that confidence level, the alpha risk, which would be convicting an innocent person. In other words, the belief is so strong to one direction, the chance that they are truly innocent is small enough we are willing to convict them. If you think about it, you know, if it's a death penalty case, there's really no appeal after the fact because it's done, so you want to have very little risk. So really in the court world, we're adjusting this decision point by whether if it's a majority, this could be at a 50% point, but we get 12 out of 12, what's the probability that that can happen for an innocent person? That's how we're drawing the decision point in this p-value curve. So really it is a hypothesis test. I hope if that wasn't enough for you, that's the best I can do, I think, at the moment, talking about why court cases are analogous to a hypothesis test. To get back to my PowerPoint, I'm basically done now. My whole thing. So I've used the at-risk add-in to try to do the simulation. I'm hoping the simulation showed a dynamic nature and showed you the other side of these. I always liked this one too when I was taught way back when. How can you forget this phrase? And this is how we were taught to get by with hypothesis tests. When the P is high, the null will fly. When the P is low, the null has got to go. Meaning you got to reject the null hypothesis if you have a low P, and you got to keep it or it'll fly for the future if it's high. All right? Maybe that's a takeaway. Now, I'd like you to score this do I understand hypothesis testing again. The poll's open. From very confused, about the same, to a lot more understanding. I want to see how we did. This is like my grade as a webinar instructor. Well, a couple people I confused, and a majority understand it a little bit better. Well, I think that sounds okay. Give another second here, Mallory will close the poll, and you'll see how we did. Pops up on the screen, and you look at 70% of your 67% did better. Well, I guess if I was to put a hypothesis test on that, I did change the mean. The knowledge of hypothesis test is increased. I don't know what p-value I'd put on that. There's my question. So what have we covered? General hypothesis testing. I tried to make pictures. I tried to use a simulation. I tried a lot with words. But again, the goal of this was to increase your understanding of hypothesis testing so when you use them, you'll better understand the decision that you're making. For 70% of you, I succeeded. For the rest of you, my hope is that it just takes time to sink in and it'll come to you later. That's all I have. If you have any additional questions, please type them. Or even questions that you may have that you might understand it differently. Let's talk about it.
Okay, we have a question.
All right.
Because there are practical limits to the sample size you can use for a large population, doesn't limiting the type 2 error require you to use an alternative condition further away from the H0 value? This can result in test rates, I believe. Test rats. Okay, this can result in test rats being fed oodles of test substance to make sure you see a significant difference if it's there.
Yeah, I'm going to paraphrase what I think the question is. Because of this alpha and beta risk, if you only have a small sample that you can take, you must drive a huge difference in the factor before it is detectable, and that is correct. It's a trade-off between how much of a change you make, what your risks are, the alpha and beta, and what your sample size is allowed. Now, that is true. And in some cases, and gave a study of rats and feeding them, I think back, I'm older, tried cyclamates, which was the very first non-sugar sweetener, They found that when you submerged a rat in it, he died, therefore it must be poisonous. They took it off the market. Further testing showed that it's safer than some of them that have come since then, but because of the way they did it, it's gone. But again, you have to have a huge difference with small samples. Now, in a Lean Six Sigma project, we teach you that even though there's these sample size calculators, we really don't use them that much. Because more often than not, we're limited by factors other than confidence and power in our sample sizes. There's a time factor. We only get a week to collect data. That limits how much I can collect. So more often than not, cost or time drives the sample size more than the statistics. But again, if it's a big change, you need very little data to show there's a change. The smaller the difference, the larger the N there has to be to detect it. Any more questions?
No, we still have a couple minutes.
Okay. Was that, first of all, whoever asked, did that answer your question? Because I don't know if that was as much a commentary of the risks of some of the testing they do today. All right? It is a tough thing to understand because it's about uncertainty. And this is when I tell a black belt or green belt student, whenever you make a decision, never say you're sure. Because every decision we make has risk of being wrong. So really consider every decision, even non-statistical ones. Every decision's got a risk of being wrong. If you could learn more information later, in other words, a bigger sample size, change your decision. I always ask you, what's the best path to commute to work? Well, they have an answer, but they will also admit that on some days it isn't the right choice. So if I choose that path, I have, say, a 5% risk I'm wrong today because it's just that random day that traffic backs up or there's an accident. But all decisions follow that type of concept. I think we're done. I appreciate your time. I hope it was worth the time, and I appreciate you coming along. There are other webinars available on our website in the resource library. Some are Lean Six Sigma. There's a couple others that are statistical. Get a chance to try it if you like them. And plus, I guess that's the table of stats. If you just want to know how you can make a stat table in Excel, it's also available on our website to download. Appreciate your time, and have a good day.
And as we mentioned before, we will follow up with you with, you will get a copy of the slides as well as the links to the recording. So thanks again for joining.